Imagine you're standing in the middle of the Great Plains. It's January. The temperature just hit negative 30 degrees Fahrenheit. Wind screams across the frozen grassland at 40 miles per hour. And you're living in a tent made of buffalo hide. Sounds impossible, right? How could anyone survive those conditions without modern heating systems, without insulation foam, without electricity? Here's what most people miss. Plains tribes didn't just survive these brutal winters, they stayed warm, comfortable even. Inside those teepees, temperatures could reach 70 degrees while a blizzard raged outside. They accomplished this through ventilation engineering so sophisticated that modern architects still study it today. But here's the mystery that puzzled researchers for decades. How did adding more airflow make the space warmer? And why did the coldest nights require the most ventilation? The answers reveal a heating system that defies everything we think we know about staying warm. The teepee wasn't just shelter. It was a precision-engineered climate control system that worked with physics, not against it. Every pole, every seam, every flap served a specific thermodynamic purpose. The Lakota, Cheyenne, Blackfoot, and other Plains nations spent thousands of years perfecting these designs. They understood principles of convection, draft control, and radiant heat that European settlers wouldn't discover for another century. Today, we're breaking down 7 ventilation techniques that transformed a simple hide tent into a winter survival machine. Each one builds on the last, and by the end, you'll understand the complete system that kept entire families alive through months of sub-zero conditions. Let's start with the first technique. Light a fire inside a sealed tent during winter, and you face an impossible choice. Keep it sealed tight, and you suffocate from smoke within minutes. Open it up, and all your heat escapes into the frozen air. Plains tribes solved this with adjustable smoke flaps at the teepee's apex. These weren't simple openings, they were aerodynamic surfaces that created a Venturi effect, actually pulling smoke up and out while preventing cold air from pouring back down. 2 exterior poles controlled these flaps independently, allowing precise adjustment based on wind direction. When positioned correctly, outside wind would skim across the flaps at an angle, creating negative pressure that sucked smoke through. The genius was in the geometry. The flaps overlapped slightly, forming a channel that accelerated airflow naturally. On the coldest nights, when you needed maximum fire, you'd open these flaps wider, not smaller. This seems backward until you understand the complete system. More smoke extraction meant you could burn a bigger fire. A bigger fire produced more heat than was lost through the larger opening. The net result? Interior temperatures that stayed remarkably stable even when exterior conditions plummeted. The Crow people could identify tribal affiliation by observing smoke flap positions from miles away. Different nations had signature adjustment techniques, but each variation served the same purpose: controlled extraction without heat loss. But smoke removal was just the beginning. The real innovation happened at ground level, where a hidden air channel changed everything. Once you solve smoke removal, you face the draft problem. Cold air needs to enter somewhere to replace rising warm air, but direct drafts at ground level would freeze anyone sleeping near the walls.
Imagine you're standing in the middle of the Great Plains. It's January. The temperature just hit negative 30 degrees Fahrenheit. Wind screams across the frozen grassland at 40 miles per hour, and you're living in a tent made of buffalo hide. Sounds impossible, right? How could anyone survive those conditions without modern heating systems, without insulation foam, without electricity? Here's what most people miss. Plains tribes didn't just survive these brutal winters, they stayed warm, comfortable even. Inside those teepees, temperatures could reach 70 degrees while a blizzard raged outside. They accomplished this through ventilation engineering so sophisticated that modern architects still study it today. But here's the mystery that puzzled researchers for decades. How did adding more airflow make the space warmer? And why did the coldest nights require the most ventilation? The answers reveal a heating system that defies everything we think we know about staying warm. The teepee wasn't just shelter, it was a precision-engineered climate control system that worked with physics, not against it. Every pole, every seam, every flap served a specific thermodynamic purpose. The Lakota, Cheyenne, Blackfoot, and other Plains nations spent thousands of years perfecting these designs. They understood principles of convection, draft control, and radiant heat that European settlers wouldn't discover for another century. Today, we're breaking down 7 ventilation techniques that transformed a simple hide tent into a winter survival machine. Each one builds on the last, and by the end, you'll understand the complete system that kept entire families alive through months of sub-zero conditions. Let's start with the first technique. Light a fire inside a sealed tent during winter, and you face an impossible choice. Keep it sealed tight, and you suffocate from smoke within minutes. Open it up, and all your heat escapes into the frozen air. Plains tribes solved this with adjustable smoke flaps at the teepee's apex. These weren't simple openings, they were aerodynamic surfaces that created a Venturi effect, actually pulling smoke up and out while preventing cold air from pouring back down. 2 exterior poles controlled these flaps independently, allowing precise adjustment based on wind direction. When positioned correctly, outside wind would skim across the flaps at an angle, creating negative pressure that sucked smoke through. The genius was in the geometry. The flaps overlapped slightly, forming a channel that accelerated airflow naturally. On the coldest nights, when you needed maximum fire, you'd open these flaps wider, not smaller. This seems backward until you understand the complete system. More smoke extraction meant you could burn a bigger fire. A bigger fire produced more heat than was lost through the larger opening. The net result, interior temperatures that stayed remarkably stable even when exterior conditions plummeted. The Crow people could identify tribal affiliation from observing smoke flap positions for miles away. Different nations had signature adjustment techniques, but each variation served the same purpose: controlled extraction without heat loss. But smoke removal was just the beginning. The real innovation happened at ground level, where a hidden air channel changed everything. Once you solve smoke removal, you face the draft problem. Cold air needs to enter somewhere to replace rising warm air, but direct drafts at ground level would freeze anyone sleeping near the walls. The dew cloth was an interior liner that hung from shoulder height to the ground, creating a double wall system with a critical gap at the bottom. This wasn't insulation in the modern sense, it was an air management system. Cold, fresh air entered through the gap between the outer teepee wall and the ground, then flowed upward through the space between the 2 layers before entering the living space near the ceiling. By the time this air reached the interior, it had been preheated by rising warmth from inside. Think of it like a heat exchanger in modern HVAC systems. The warm interior air transferred energy to the cold incoming air through the buffalo hide membrane separating them. This channel served multiple purposes simultaneously. It prevented condensation from forming on the inner surface, which would drip onto sleeping families. It eliminated ground-level drafts entirely, and it recovered heat that would otherwise escape through the walls. During extreme cold, families would pack snow or dried grass into the gap at ground level, further restricting airflow to just what was needed for the fire. The dew cloth also created a dead air space that provided actual insulation. Buffalo hide isn't particularly insulating on its own, but trapped air between layers is one of nature's best insulators. Here's the detail that changes everything. The dew cloth extended higher on the windward side, creating asymmetric airflow that prevented backdrafts. This was empirical fluid dynamics perfected over generations. But controlling airflow meant nothing if the fire itself wasn't positioned correctly, which brings us to the technique that shocked modern engineers. We're just getting started with the surface-level techniques. Coming up next, the fire placement secret that seems to break the laws of physics. Common sense says to place your fire in the exact center of your shelter for even heat distribution. But in a teepee, a centered fire creates cold spots and smoke problems that make the space nearly uninhabitable.
Plains tribes positioned fires slightly off-center toward the back and typically on the windward side. This asymmetric placement worked with the natural convection currents created by the teepee's cone shape. Warm air rose along the slanted walls in a spiral pattern, not straight up. By offsetting the fire, they encouraged this spiral to complete a full circulation before reaching the smoke flaps. The typical offset was about 18 to 24 inches from true center. This small adjustment meant the difference between constant smoke irritation and crystal clear air. The fire's position also determined how heat reflected off the inner walls. Teepee walls weren't vertical, they curved inward, creating a parabolic reflector effect. An off-center fire bounced radiant heat in a controlled pattern that bathed the entire floor space evenly. But here's what makes this truly sophisticated. The offset direction changed based on seasonal wind patterns. Winter winds on the northern plains typically blow from the northwest. Placing the fire toward the northwest section created a buffer zone where the coldest drafts passed through empty space before encountering the living area. The fire itself acted as a thermal curtain, warming any incoming air before it reached sleeping spots. Archaeological evidence shows fire pits positioned with remarkable consistency, suggesting this wasn't random adaptation, but carefully transmitted engineering knowledge. Stones surrounding these fire pits were arranged in specific patterns that directed heat downward into the earth, creating a thermal mass that continued radiating warmth long after the fire died down. Fire placement created the foundation, but the real temperature control came from a material most people would throw away. Buffalo hide provides weather protection, but offers minimal insulation value. A single-layer hide teepee in sub-zero conditions would still feel brutally cold despite a roaring fire. During autumn, plains tribes collected the loose undercoat hair shed by buffalo herds. This fine wool-like hair, distinct from the coarser outer guard hairs, became the secret insulation ingredient. Women would stuff this hair between the outer teepee cover and the dew cloth, creating a layer 3 to 4 inches thick. Buffalo wool has a lower thermoconductivity than sheep's wool due to its crimped structure that traps more air pockets per cubic inch. But installation wasn't random. Hair density varied by section, thicker on the windward side and near ground level where heat loss was greatest. The top third of the teepee walls received less insulation because rising heat needed somewhere to go. Too much insulation at the top would trap smoke and create dangerous carbon monoxide buildup. This gradual density change created a thermal gradient that encouraged proper air circulation while retaining warmth where families actually sat and slept. The buffalo hair had another unexpected property. It was naturally fire-resistant when tightly packed. Loose hair would ignite easily, but compressed wool-like material charred slowly, providing crucial seconds for fire control if sparks escaped the fire pit. Winter storms often brought lightning, and a lightning-struck teepee had better survival odds with this built-in fire suppression. Families replaced this insulation annually as winter weather and moisture degraded its effectiveness over time. Old insulation was never wasted. It became stuffing for bedding, winter moccasins, or trade material. The effort required to gather and install this hair was substantial, but it could mean the difference between surviving winter and freezing during the first major blizzard. Some nations supplemented buffalo hair with cattail down, dried prairie grass, or sage, but buffalo hair remained the gold standard for thermal performance. Its crimped fibers didn't mat down under compression the way plant materials did, maintaining loft and insulation value throughout the winter season. This insulation system worked brilliantly, but it required one more element that modern science only recently validated. Even with perfect wall insulation and air management, heat escapes relentlessly through the ground, especially in frozen soil that acts as a massive heat sink, drawing warmth downward. Plains tribes created elaborate ground seals using materials layered in specific order for both insulation and thermal mass. First came a layer of dried prairie grass or sage, pressed flat and extending about 2 feet beyond the teepee's base circumference. This created an initial insulation barrier against frozen earth. Next came buffalo robes laid fur side down, the thick leather acting as a vapor barrier, preventing ground moisture from rising into the living space. But the genius was the third layer, a scattered arrangement of river stones, each about fist-sized, placed in a circular pattern around the fire pit and extending outward. During evening hours, these stones absorbed radiant heat from the fire. Throughout the night, they released this stored thermal energy slowly, creating a warmed floor surface that prevented heat loss through the ground. This thermal mass effect meant that even if the fire died down to coals during sleep, the floor remained warm enough to prevent dangerous heat loss through contact.
Winter camps were specifically chosen near river valleys where these smooth stones were abundant. The stone layer served multiple purposes. It prevented the hide walls from getting soaked by ground moisture, created air channels that improved underfloor ventilation, and provided thermal stability that smoothed out temperature fluctuations. When morning came and the fire was rebuilt, these stones heated quickly, establishing comfort faster than would be possible with cold ground. The grass robe stone sandwich created an R value equivalent to modern insulated concrete floors. Archaeological sites show circular stone patterns perfectly matching teepee dimensions, evidence that this technique was standard across multiple plains nations. Some families heated specific stones in the fire before bed and placed them in sleeping areas, a proto-radiant floor heating system that kept feet warm during the coldest hours. During spring breakdown, these carefully arranged stones were left in place, marking winter camp locations that could be reused year after year. The grass layer decomposed and enriched the soil, while the stones remained ready for the next season's camp. Ground sealing controlled heat loss downward, but there was still one massive vulnerability that could negate everything: the entrance. The entrance problem nearly destroyed everything these techniques accomplished, but the solution was the most elegant engineering of all. A teepee needs an entrance large enough for people to enter carrying firewood, food, and supplies. But every time someone opens that door during a blizzard, precious heat escapes and freezing wind pours in, dropping interior temperatures by 10 to 15 degrees in seconds. Plains tribes developed a double-door vestibule system that functioned as an airlock centuries before the term existed. The outer door was the primary hide flap, oriented to open away from prevailing winds, but 2 to 3 feet inside, a second hide curtain hung from internal frame poles, creating an enclosed buffer zone. This vestibule trapped cold air between the two barriers, preventing it from flooding the main living space. When entering during extreme weather, you'd open the outer flap, step into the vestibule, close the outer flap, wait 2 to 3 seconds while the vestibule air stabilized, then open the inner curtain.
This two-step process reduced heat loss by approximately 70% compared to a single-door entry. The vestibule space also served as cold storage during winter. Fresh game, snow for water, and supplies that needed to stay frozen were kept in this zone. But the sophistication went deeper. The vestibule walls weren't parallel, they angled outward slightly, creating a funnel shape. This geometry did something unexpected. When wind hit the outer door, the funnel directed pressure around the entrance rather than straight through it. The slight outward angle created an eddy current that actually pushed against incoming air, providing passive wind resistance even when both flaps were momentarily open. Some families hung dried grass bundles or small hide panels inside the vestibule, creating additional wind baffles that broke up direct drafts. During severe storms, these could be adjusted to create a maze-like path that wind couldn't follow efficiently. The Blackfoot people developed elaborate painted symbols on inner door curtains that served as visual reminders of proper entry protocol, critical when children needed to remember the two-step process during emergencies. The vestibule also prevented the psychological horror of wind-blown snow entering the living space. Even a small amount of snow penetration could damage interior belongings, wet clothing and bedding, and create dangerous conditions. By containing all-weather entry in the buffer zone, the main space remained pristine and dry even during multi-day blizzards. Winter travelers approaching a camp could identify experienced versus novice teepee setup by observing entrance arrangements from a distance. A properly constructed vestibule had specific proportions and angles that signaled engineering knowledge. 6 techniques down, but we've saved the most counterintuitive for last, the one that confused scientists until computer modeling finally proved it worked. Occasionally, conditions become so extreme that normal ventilation systems can't cope. Sudden temperature drops, wind direction shifts, or unexpected snow accumulation could create carbon monoxide buildup, backdrafts, or structural stress that threatened everyone inside. Every traditionally constructed teepee included emergency ventilation ports positioned at strategic points around the structure's midsection. These weren't regular openings, they were reinforced slits backed by additional hide flaps that could be opened independently. During normal conditions, they remained sealed, invisible to anyone unfamiliar with their location. But when needed, they transformed the teepee's ventilation from a fixed system to a fully adaptable one. The placement of these emergency ports followed precise mathematics. They were positioned at 60-degree intervals around the circle, aligning with structural support poles. This distribution meant that regardless of wind direction, at least 2 ports would be positioned optimally to create cross-ventilation without creating direct drafts across the fire. Computer modeling in the 1990s confirmed what Plains nations knew empirically. This 60-degree spacing created pressure differentials that maintained fire draft even when main smoke flaps became blocked by ice or snow. But here's what shocked modern engineers. Opening these emergency ports during the coldest weather sometimes increased interior warmth. This seems physically impossible until you understand the complete airflow system. When smoke flaps became partially blocked, the fire would smolder rather than burn cleanly, producing less heat. By opening emergency ports, you restored proper oxygen flow to the fire, allowing it to burn hotter and cleaner. The additional heat generated exceeded heat lost through the extra openings, net positive warmth. These ports had another critical function during ice storms. Freezing rain could cement smoke flaps shut within hours, creating a death trap. Emergency ports provided backup ventilation that prevented suffocation if main systems failed. Elders taught children the locations and proper use of these ports as early survival training, knowledge that saved countless lives during unexpected weather events. The reinforced construction around ports was actually stronger than the regular hide covering. Rather than weakening the structure, they acted as stress relief points that prevented tearing during high winds. This counterintuitive design, adding holes to increase strength, reflects deep understanding of material stress and failure modes. Archaeological evidence of port systems is subtle but present. Wear patterns on surviving teepee poles show rope grooves at exact intervals matching emergency port positions. Ethnographic records describe elaborate signals and protocols for emergency port deployment, suggesting this was sophisticated group knowledge rather than improvised survival tactics. Here's what researchers finally understood after years of studying these techniques. Each element wasn't independent. They formed an integrated thermal management system. The smoke flaps pulled air upward. The dew cloth channeled it inward. The offset fire created circulation. Buffalo hair trapped warmth. Ground seals prevented loss. The vestibule blocked weather. Emergency ports provided redundancy. Remove any one element and the entire system degraded. But together, they created a shelter that could maintain a 40 to 50 degree temperature differential between inside and outside. That's 70 degrees indoors when it's -30 outside, achieved with nothing but fire, hide, and brilliant engineering. Modern studies comparing teepee thermal performance against similarly sized canvas tents found teepees maintain temperature 53% more efficiently. Some architectural firms now study Plains tribe ventilation principles for designing low-energy buildings in extreme climates. Those two questions from the beginning, more ventilation worked because it enabled bigger fires, and cold nights required it because that's when you needed maximum heat generation, which required maximum oxygen flow. The teepee wasn't primitive, it was perfected. Which technique surprised you most? The emergency ports, the offset fire, or something else entirely? Drop a comment with your answer. I read every one. And here's a question. Could any of these principles work in modern housing? If you've tried adapting indigenous engineering for contemporary use, share your experience below. Subscribe for more deep dives into forgotten engineering that changed human history.